This is the pre-lecture video for the second part of Chapter 2. Moving beyond the periodic table we saw in our previous video, we move towards compounds and molecules. Let's discuss chemical formulas. So a chemical formula describes the number of atoms that are bonded together to make up one molecule of a given substance. We see hydrogen has a formula of H2, so we have two hydrogens, two oxygens comprised a molecule of oxygen. Water, H2O, different from hydrogen peroxide with the second oxygen, H2O2. Carbon monoxide, carbon dioxide have a different number of oxygens attached to a carbon atom. We see different types of hydrocarbons with methane and ethylene, and really there's a tremendous number and varieties of molecular compounds. Let's quickly compare two different types of compounds. Water is a molecular compound, has a melting point of 0 degrees C. NaCl is best classified as an ionic compound with a melting point of about 800 degrees C. Clearly we have a very different property between the melting points of these compounds. But let's take a little bit closer at why we have such a difference. NaCl forms what we call ions when it forms a compound. You get a plus charge on sodium, a minus charge on the chlorine atom, and then you get a really strong electrostatic force of attraction between the ions. What ends up happening is your ions pack closely together within a crystal of sodium chloride, and then those ions are really hard to separate from each other, hence why the compound has a high melting point and a high boiling point. What happens in the crystal, if you were to take a look at where the atoms and how far apart they are relative to each other, if you take a look at a couple of ions of sodium and chloride over here, what you'd find is that you couldn't spot a molecule of NaCl. Instead, you'd have two ions here, another ion, all in as close proximity as they could possibly get to each other, which in NaCl works out to be about 2.4 angstrom, meaning your adjacent ions have exactly the same bond distance throughout the crystal. So you really can't spot a molecule of NaCl. Really, you just have a repeating three-dimensional network of these ions comprising this solid material, or the solid compound. Now, if you compare that with ice, with water at temperature below 0 degrees C, what you'd have are individual water molecules, where you have one water and a second water molecule, and of course a lot more, but their contact would be further, a lot greater separation between the O and the H of two adjacent water molecules compared to the contact between the hydrogens onto the oxygen comprising one molecule. So about 1 angstrom separates the H and the O in a water molecule. Same thing for your second water molecule, but about 1.9 angstrom then separates the two water molecules from each other. So they're not forming as close of an interaction. They're not forming this type of network of plus-minus repeating charges like ionic compounds. So the result is water has a lower melting point than sodium chloride. So ionic compounds result whenever we have plus and minus charged ions, and then the stronger electrostatic force of attraction between those ions give ionic compounds their properties of having higher melting points and boiling points than most of the molecular compounds, or most common molecular compounds. So let's discuss different types of formulas. We have empirical formulas and molecular formulas. Let's give a quick example of a molecular formula and picture a compound. Let's say we are working with hydrogen peroxide. The formula of hydrogen peroxide is H2O2. So for hydrogen peroxide, you could express the simplest ratio of the atoms in the compound. That would be HO. So HO, this would be the empirical formula, the simplest ratio of the atoms in hydrogen peroxide, but H2O2 would be the molecular formula. So the molecular formula for a molecular compound really tells us all the information we would want to know, the specific count of each of the atoms, each of the elements comprising the compound. The empirical formula really doesn't tell us a whole lot, but what we'll see in Chapter 3 is that experimentally you can do an experiment to find an empirical formula, and then from that experiment work out what the molecular formula is. So we'll see empirical formulas and molecular formulas pop up in the next chapter again. Now there are a variety of ways to picture molecules. We use formulas a lot in chemistry. We'll see that those feed into structural formulas. We'll be able to sketch these and start coming up with ways of writing Lewis structures in Chapter 8 for a variety of different compounds. We can also then start thinking three-dimensionally. How are the atoms actually situated in three-dimensional space? That's a topic we get into in Chapter 9. We could talk about ball and stick models where you're kind of picturing each of the H's or an atom. You can make that a ball. They're connected with a single bond to the central atom. So we have a single bond connecting all those atoms. That's our ball and stick model. And sometimes we use space-filling models. The ones we're going to see in this class really how to work with the most are probably our molecular formulas, and as we get into chapters 8 and beyond, structural formulas and three-dimensional shapes. So now in our discussion earlier on ionic compounds, we didn't exactly say a whole lot of what types of atoms or elements tend to form ionic compounds, but we're going to see in chapter 7 that it's going to be the atoms that most easily lose electrons. Those are our metals, and the easiest group of elements that lose electrons are the alkali metals. The next group of elements that give up electrons would be the alkaline metals, and then we'll also see transition metals losing electrons to form stable cations. Then those cations can pair up. They can give their electrons to our non-metallic elements that then pick up electrons and form negatively charged anions. And then they can stick together after they ionize. So we can go through a couple quick examples, like KCl, for example, would be an ionic compound, potassium chloride. We could have strontium, let's say bromide, but you're going to need 2 bromide minuses to cancel out the 2 plus charge. The one thing that we see is that the noble gases are the elements that have an especially stable electron count. So they're the elements that have a stable electron count and don't need to add or lose electrons to gain stability. Fluoride has to gain an electron to come up with that noble gas count. Oxygen's group of elements has to pick up 2 electrons. Nitrogen's group would have to pick up 3 electrons to arrive at that noble gas configuration of electrons. So if you were to look at, for example, neon. Neon has 10 electrons. Fluorine, without a charge, has 9 electrons. F minus picks up that extra electron to obtain that same number of electrons as neon. Likewise, sodium and magnesium. Sodium has 11 electrons, magnesium has 12, so sodium can lose 1 to form Na+, 10 electrons. And likewise the same for magnesium losing 2 electrons. This chart here is showing some common ions. H plus is the hydrogen ion. You see sodium plus sodium ion, potassium ion. Really easy to name these two because it's just the element name followed by ion. We see an example of ammonium, NH4 plus. Notice the IUM ending is common for most of our positively charged ions that are common. We also see this for a lot of metal atoms end in the IUM suffix. What's really important to know is for our metallic elements, they can only form cations. Metals are never going to gain electrons and form minus charged anions. So we see here some common cations with a +2 or a +3 charge. So we see our alkaline metals, which we know form a stable +2 charge. We see zinc and cadmium across the transition metal series. These transition metal elements only form metals with that particular charge state. We see a few metals form more than one type of charge state. This is common for a lot of our transition metals. So for like cobalt and copper and iron, you see a Roman numeral listed. That Roman numeral 2 is signifying the charge on that cation. So cobalt 2 is cobalt with a +2 charge. We don't really use in this class this ic or us nomenclature system, so you don't have to know any of these more historical names, but you may have seen them at some point for, iron 2 being ferrous, iron 3 being ferric. We will always name our ions iron 2 or iron 3 with the Roman numeral system. So it's a really simple system. If you have, say, manganese 5, that would be manganese with a +5 charge. The Roman numeral is just telling you the charge of the metal in the compound. This slide shows some common anions. We see H- hydride, F- fluoride, Cl- chloride. You might be noticing that our atomic anions, the ones that have just a single atom, commonly end in the IDE suffix. If we see some collections of molecular ions, they take some more historical names, like cyanide ion, hydroxide ion. O2 2-, that's just oxide, that's oxygen with the 2- charge, but put 2 of them together, that's peroxide as a molecular ion. Now, molecular ions have their atoms attached in a covalent way, just kind of like water, but where the covalent ion ends up with an overall charge. So our O2 2- is really just two oxygens bonded together with a bond like in a molecular compound, but where the unit ends up with an overall minus charge. We also see this a lot with oxygen bonding to nonmetal elements like chlorine and nitrogen for chloride ion, perchlorate ion, nitrate ion. We also see it happen with carbon for carbonate. Metals as well, permanganate ion, MnO4-, dichromate and chromate ions. We see sulfate and phosphate ions, kind of wrapping out this particular chart. If we look back to ammonium from the cation chart, that would be nitrogen with 4 hydrogens attached, overall plus charge spread across the molecule. Sulfate, essentially the same thing, but with 4 oxygens spread across the sulfur with a 2- charge. And so if we had ammonium sulfate, we would just have to have 2 of the ammonium cations and just 1 of the sulfates. So if we're going to write the formula for ammonium sulfate, ammonium 2, SO4. Now, writing formulas, pretty simple when we consider the charges of our ions. Magnesium, that's an alkaline metal, 2+ charge. Nitride, 3 over from neon, that's a 3- charge. So we're going to need 3 magnesiums and then 2 of the nitrides to balance out our charge overall, such that the entire compound is overall charge neutral. It's really hard to build up charge. If you build up too much charge, you're going to have a lightning strike. So you're not going to see compounds exist with an overall charge. For a compound to exist, it has to be charge neutral. Okay, so magnesium nitride Mg3N2. We can do a couple more examples. Let's compare and contrast oxide ion and peroxide ion pairing up with something like sodium. So you have sodium plus in both of these cases. Sodium only forms a +1 charge. That's the only type of ion you get with sodium. But oxygen, you see, you get O2 with a 2-, or just a regular O2 with a 2- charge. Now remember, this is oxide, and then this one is peroxide. So just 2 different ions altogether. Okay, so if we have a 2- charge, we're going to need 2 of the pluses to balance out the 2-. So Na2O is what we call sodium oxide. And then for the peroxide, we're going to need 2 of the pluses to balance out the O2 2-. So the formula here ends up would be Na2O2. So a different formula, should have a different name. So the name here is sodium peroxide. So nomenclature is going to be a big part of this chapter, and it's going to help us recognize different types of compounds through our task of trying to learn how to name them. So our naming, the types of compounds we're going to go through and learn a systematic approach for naming. Ionic compounds, we'll go through acids. Acids we will recognize as anions, where H+ has been added onto them. And really what an acid is, we'll see later in chapter 4 and beyond into chapter 16, is that acids are compounds that when they're dissolved in water end up releasing H+ ions. So something that releases H+ should probably contain an H+ ion, so they can release it upon being dissolved in water. Then we'll name some binary molecular compounds. Sounds complicated, but that's just compounds like carbon monoxide, carbon dioxide. Then we'll also go through a couple of different types of simple organic compounds, like alkanes and alcohols. So we've been using this simple inorganic ionic compound nomenclature system a few times already, but our compounds are named by the cation name followed by the anion name, and by our understanding of the charges of these ions, that's how we account for the subscripts in the compound. So when we're naming something like AlCl3, we pick this up at recognizing we have a 3+ aluminum, minuses for the chlorine atom. The only charge aluminum forms is +3. The only charge we get on chlorine is a -1. So we pair this together. This compound is the name of the cation, aluminum. aluminum cation, but this would be aluminum, and then the name of the anion, chloride. Now notice, the key here is just pointing out that we're not calling this aluminum trichloride. We don't need to stress the tri, because as long as we know aluminum and chloride are a metal and a nonmetal, so they're going to form one of these ionic compounds. We're going to get the stable cation of aluminum, 3+, and then the stable anion of the nonmetal element chlorine, which would be chloride with a -1 charge. Let's pick up some systematic ways of naming compounds. Now, an oxyanion is wherever you have some type of central atom with oxygens attached to it, where you have some number of oxygens with some type of a charge. Okay, now nitrogen forms the most common oxyanion with 3 oxygens and a -1 charge. Sulfur goes with 4 oxygens and a -2 charge. That's just nature. We're just memorizing those formula and those names. Now, the systematic way of naming the case where we've lost an oxygen, if you drop an O off of those formula, go to NO2, but still a minus, SO3 still a 2-, we're not changing the charge off of these representative anions, we're just changing the oxygen count. All we need to do is change that ending to ITE. So a very easy systematic way to learn how to name some additional ions from those which we might memorize. At the end of our discussion and naming, I'm going to go through a summary of all the ions we have to memorize. So let's look at an example here using chlorate. That's ClO3-. So that's the most common representative oxyanion of chlorine. Drop an O, we saw in the previous slide. Let's go to ClO2-, that should become chlorite. Change 8 to ite. And then if you drop and lose a second oxygen, this anion can exist with the formula ClO-. The representative name here would be hypochlorite. So we introduce the hypo out in front. Then likewise, if you add an oxygen onto your base representative formula, go to ClO4-, then notice the only thing we change with our name is we add the PER, the per suffix. We've actually already used this rule when we had gone from having oxygen, the oxide ion, with a -2 charge, that when this ion simply picked up a second oxygen to go to O2 with a 2- charge, that we went from oxide and then just added the per out in front to peroxide. So in a way, we've already used this rule, maybe without defining it carefully. Now we might pick up a couple of things. One is that for something like nitrate, which we saw in the previous slide, it only really has these 2 oxyanions that actually exist in nature. It just doesn't have the NO- example, and NO4- just isn't something that actually exists with nitrogen. Now, if you go down to bromine, and you know that bromate ends up being BrO3-, then you can go name BrO2-, which actually exists. BrO- exists, we can name that. BrO4- exists, we can name that. And so it just lends itself to a simple rule that if we know bromate's BrO3-, then we know this is ite, this is hypo, ite, and then this is per, and then sticking with that ATE ending, per bromate. So we really don't need to memorize these 3 ions here. We just have to memorize that bromate's BrO3-. Now really that's just periodicity. If chlorine forms a stable oxyanion with 3 oxygens and a minus, bromine's probably going to do the same, and iodine does as well. So iodine forms the most representative oxyanion, iodate, with the same type of general formula. And then likewise, it also exists in nature as all 4 of these possibilities. Now, we're not trying to memorize or understand why that's the case. We're just really trying in this unit here in nomenclature to be able to understand the types of formula that are common for ionic compounds, and then be able to name, if we're given a formula, what the compound is. So be able to name a compound given the formula, or be able to write the formula if we're given the name. So here we see a summary of the anions that we're expected to memorize and know. And the red are the ones that we should be able to determine just from simple conventions. So our atomic ions, just one single atom, those are named really easily. It's just the root name of the element followed by IDE. So hydride is one that catches people off guard sometimes, but just hydrogen, minus charge, so hydride. Likewise, oxygen, oxide, so very easy. Superoxide is actually the O2 with just a minus charge. So if we have O2 with a -1 charge, superoxide, and if we have O2 with a 2- charge, that's peroxide. hydroxides, OH minus, acetate, two different ways of writing the formula, CH3, COO minus. This is a little bit more structural information written this way. This might make more sense after we see chapter 8, or if you remember kind of the Lewis structure of this ion. But the writing it, all the atoms together, C2H3O2 minus also suffices for acetate. Carbonate, CO3 minus, nitrate, NO3 minus, phosphate, PO4 3 minus, sulfate, SO4 2 minus. I've heard all kinds of goofy songs people have for remembering how many oxygens there are in the charge, and I can't remember the song, but it's one if you can memorize the song. I'm pretty certain you can just memorize that these are our common representative anions that have that ATE ending on the root name of the element. Or you can just memorize nitrates NO3 minus. Drop an O, nitrite, drop an O, phosphite, drop an O, sulfite, likewise drop an O. Carbonite, very easy. The chlorate, bromate, iodate are the ones that go the full series of having the full 4 possibilities to take advantage of our nomenclature system. So we're not really memorizing the extra ones in red. We're just kind of learning our nomenclature system and applying it to chlorate, bromate, and iodate. We can also, we haven't talked about this on a slide yet, but you can add hydrogen as an H plus ion onto anything that has a 2 minus charge or greater and still have an anion. And so that is an example of an anion that we should be able to name. So let me write an example up here. So if you were to take carbonate with a 2 minus charge and then throw an H plus onto that, so now this ends up just now being HCO3 with a minus charge, that would be hydrogen carbonate. So you name the anion for its original name, carbonate, and then just hydrogen out in front. Okay, so hydrogen carbonate would be HCO3 with a minus charge. Now we're going to see in a moment that if you neutralize the charge fully and go to a neutral charge, this is going to be something we name as an acid. So that's going to come up in our next nomenclature system. That would not be something that's an example of an anion. Now, phosphates and phosphites have a 3 minus charge, so you can actually add H plus twice. You go H plus onto phosphate. That knocks the charge down to 2 minus. You can add that second H plus, H2PO4 minus. Now that would be dihydrogen phosphate. So we have hydrogen phosphate, HPO4 2 minus, and then dihydrogen phosphate, H2PO4, now just a minus charge overall. So we should be able to work the charges out here, the formula, just from our understanding of what phosphate is, and the idea here that we're adding H plus ions onto those formula. Now if we can summarize the cations that we are responsible for naming, the alkali cations, the alkaline cations, very easy, just +1 charges for the alkalis, +2 charges overall for the alkalines. Aluminum only forms a +3 cation. Zinc only forms a +2. Silver only forms a +1. We have molecular ions, ammonium plus, H3O plus, this is like a protonated water molecule, or this is H plus in water. H3O plus is hydronium. Likewise, a collection of 2 metal atoms together with kind of like a covalent linkage would be Hg2 2 plus. This looks kind of like a metallic version of peroxide ion, where you get 2 mercuries bonded together with an overall plus charge on each of them, takes the name mercury 1. So by our normal nomenclature system, if I say copper 1, you'd say copper plus. Or if I were to say, I don't know, another good choice, cobalt 1. I don't think that really exists, but that would just be cobalt with a +1 charge. But if I say mercury 1, it's not mercury with a plus, it's really 2 of them with a 2 plus. So you see on average, each one of the mercuries has a +1 charge, but they're just linked together through some type of linkage with an overall 2 plus charge. This comes up a bit in chapter 4 in some examples that we'll see. Now let's kind of quickly define what an acid is. We'll see more clearly how acids behave when we get into chapters 4 and beyond, but it's a case of just taking something like Cl- and then neutralizing the charge with an H+. Take any anion that you've learned how to name, maybe Br with a minus charge, neutralize it with an H+. Take NO3 with a minus charge, neutralize with an H+, you get HNO3. So our nomenclature system here is that if the original anion name was like chloride or bromide, had that IDE ending, then our name becomes the hydroic acid. So HCl is hydrochloric acid, and then we got hydrobromic acid and hydroiodic acid for HI. Now, if the original anion had an ITE ending, then we go to an OUS ending, and if the original anion had an ATE ending, then you go to an ic acid ending. Let's start with the ATE ending, because here we have nitrate, so this would be nitric acid. Now notice it's not hydronitric acid, it's just nitric acid. So if we review for HClO3, that's chlorate, so this would be chloric acid. And then the next one would be perchloric acid. And then the ITE endings go to OUS acid. We should be able to name all four of these acids with a different name. They're different compounds, they should have different names. ClO2 minus is chlorite, so this becomes chlorous acid. And then hypochlorite in acid form would be hypochlorous acid. So a binary compound is a molecular compound, or it's a nomenclature system we use for molecular compounds. Binary just means two elements. And since we're talking molecular compounds, they should be nonmetals. Now the reason why we're signifying this, you might look back at NaCl and say, well, that's a binary compound, contains two elements. But it's not a binary molecular compound, it's a binary ionic compound, or it's really just an ionic compound. So we call it sodium chloride. We're not going to name it with this system. This system's for naming things like CO versus CO2, or NO2 versus N2O4. So our nomenclature system here kind of begins with, I guess, pointing out that carbon monoxide and carbon dioxide are perfectly named with the system. So if you just remember or just know that our nomenclature system works perfectly here. So we have carbon monoxide and then carbon dioxide. We basically see our rules. We're not starting with mono if there's only one atom that comes first. There's one carbon, but we're not calling it monocarbon. We're just assuming there's just one if there's no mono. And then we're using prefixes to indicate the quantity of the second element. So it's not carbon oxide for one oxygen, but monoxide to stress that there's just one oxygen. Di to stress two, tri, tetra, penta, hexa. These are just your ordinary prefixes out in front. And so NO2, nitrogen dioxide, I won't bother writing that one. But N2O4, we would call that di for two, dinitrogen, tetra, oxide. Now, a lot of times, and this just gets finicky, you're not going to handwrite a lot of examples. We'll take multiple choice tests, but it's not tetraoxide. It ends up just being tetroxide to roll off the tongue a little bit better. But we're not going to try to trip you up in the nuances of spelling some of these types of compounds, but just picking up tetra for 4, di for 2, so 2NO4. Now, the idea here is there's really nothing that's going to tell you exactly how many N's and O's there should be in these formula. All different kinds of compounds exist of these varieties with nonmetals. So we just need to be able to name the different types of compounds that we might encounter involving these elements. Again, binary molecular compounds, two elements where they are both non-metallic elements. So we have a small set of organic nomenclature we review in this class. You probably know methane as CH4. Now the idea here is we're saturating carbon. Each carbon is saturated when it has 4 total bonds surrounding it. So if you have ethane where you have 2 carbons bonded together, then you only need 3 hydrogens on each side to saturate those carbons so that they each have 4 total bonds surrounding them. So ethane's formula would be C2H6, and then propane would be CH3CH2CH3, where we only need 2 hydrogens for the central carbon, and then 3 for the ones in the end. We're counting 4 bonds on each of the carbons. So a pretty clear way of writing these formulas. So the next one would be butane. So butane is just 4 carbons in a row, and then we just have hydrogens filling all of the spots to make 4 total bonds for each of the carbons. So it ends up being C4H10. And then from there, it just becomes repetitive. You're just going to add a CH2. Just adding a CH2 in the middle here. C5H12, this would be pentane. C6H14 would be hexane. And you can name all the way up to decane because we're just at the point you go from pentane, it just becomes penta 5, hexane 6, hepta for 7, the same prefixes from the previous slide, followed by that ane ending. And this is a nomenclature system for the type of compounds we call alkanes. So alkanes have that ane ending. Now, if you've already seen some OChem in high school, if you want to know where you pick up some more nomenclature in OChem down the road, alkenes would have a double bond between the carbons. Alkynes would have triple bonds between the carbons, but we're not going to worry about naming those types of compounds in Chem 1210. The last group of compounds we'll name are alcohols, so our most famous alcohol, probably ethanol. Just take one of the H's on ethane and replace it with an OH group. We go from having ethane be a gas at room temperature, now we have ethanol, a liquid up to about 78 degrees C before it boils. So ethanol is just one OH group replacing one of the hydrogens, methanol the same, one OH replacing a hydrogen on methane, and propanol is just replacing the OH on one of the carbons. So notice this one's called 1-propanol because it's on the first carbon. You can think of numbering these carbons in linear sequence. As soon as you get to propane, you actually have a choice of, is this OH going to go on the first or on the second carbon? And then the third is exactly the same as the first, so there is no such thing as 3-propanol. Let's take a closer look at this. So let's look a bit more closely at propane. So propane, you can put that OH group on one carbon or you could put it on the central carbon. These two carbons are exactly the same as each other, so it doesn't make a difference if we're going to put the OH group on the first one or what you might think is the third one. Both of those positions would be what we call 1-propanol. 2-propanol is where we put the OH on the one in the middle. 3-propanol, if you want to ever name something 3-propanol, is exactly the same as 1-propanol. So that's really not a unique compound. We name compounds that are different from each other different names. We call compounds that are the same as each other the exact same name. So if we were to write or think of the case of having our compound with OH here, that's also 1-propanol. So 1-propanol, whether it's on the first or the last carbon, it's really the exact same carbon, same compound, same name. So these are isomers of each other. Isomers are different compounds that share the same formula. So it's sometimes useful to point out that what the effect here is that these different compounds have different properties. So 1-propanol and 2-propanol have slightly different boiling points. So they do differ slightly in their properties. Similar because they have pretty close to similar structure, but not exactly the same, so slightly different properties. That wraps up our introduction to the second part of Chapter 2. There's really a lot in this unit on naming. There's a lot of nuance with naming. Once you kind of have the formula down pat, the types of compounds that you tend to see are pretty simple. When you're naming compounds, I think the biggest thing you can try to do is first try to imagine the type of compound you're naming. Is it a ionic compound? Is it best described as being an acid? Is it a binary molecular compound, or is it an alcohol or an alkane? And then from there, you should be able to fairly easily fit that compound into its proper name, its naming conventions for the types of atoms that are involved, and hopefully from there give a perfect name for the substance. We'll see some examples in class. We'll see a lot of examples in the homework, and hopefully they'll start to make sense after a little bit of practice. All right, thank you for the attention.